The geometric characterization of the ellipse, similar to the one that we had for parabola, is the following. It is a set of points in the plane such that the sum of distances from them to two fixed points which we will call f1, f2, and they will be foci of the ellipse is constant. So the sum of distances from any point of the ellipse to two fixed points must be the same regardless at which point you're looking. So let's say we choose our system of coordinates so that the foci are placed at equal distances away from the origin. So we have origin right here, and the f1 and f2 are symmetric with respect to it on the x-axis. And then we are looking at a point P somewhere on the ellipse, coordinates x, y. Then regardless at which point we are looking, these two distances from P to f1 and P to f2 should always add up to the same number. So in formulas, it would go like this: P to f1 plus P to f2 must be always the same. So here A is a positive constant. And so the reason for putting 2 here will follow from some computation that we need to carry on in a second. And basically it makes the resulting equation for the ellipse very nice. And so the idea is then that regardless at which point of the ellipse you're looking, so this will be the ellipse, and then for any other of its points, say this one, if you add up the two distances to the focus f1 and f2, their sum is again 2a. So this, by the way, gives a neat way to draw perfect ellipses. So think of the foci f1 and f2 as pins stuck into the cardboard of the plane, and then think of a piece of thread that connects f1 to f2. And then if you place a pencil here at the point so that this pencil stretches the thread, so it's tight here and here, and then make the pencil move around, you will trace an ellipse such that the length of the thread corresponds to the value of the constant 2a, because the sum of the two distances to your pins will be precisely the length of the piece of thread here. And so the idea is that using this equation and the fact that you chose the coordinates of the foci to be symmetric, so let's say f1 and f2 are of the following form. So they are symmetric with respect to the origin and lie on the x-axis. So using these expressions for f1 and f2, you can rewrite this using distance formula like so. So the sum here is the following expression. We have distance from the point xy to f1, which is x plus c squared plus y minus 0 squared plus another square root. And here we have x minus c squared plus y minus 0 squared equals 2a. And then square both sides. So basically, just to outline what you should do, move this to the right hand side, then square both sides, simplify, and again, if you allow me not to go into further details, the result of these computations is that you end up with the following. You will have x squared divided by a squared. So this is the same a you had for the sum of the distances here. X squared over a squared plus y squared over a squared minus c squared equals 1. And so here c is, remember, the distance from the origin to either of the two foci. And if you denote a squared minus c squared equals b squared, the result of that is precisely the equation of the ellipse as we know it from our previous discussion as well as from pre-calc. Okay, and so this is the equation of the ellipse with let's say with the foci plus minus c 0. The foci are in the horizontal axis, with the c squared equal to a squared minus b squared. So that is what you get if you recall the way we introduced b squared. And vertices plus minus a 0. So by vertices, for the ellipse, we mean the x-intercepts. So these two points here and here are going to be the vertices of the ellipse. And it's not hard to check that because of the way we introduced a, their coordinates are indeed a0 and minus a0. Great, so we have characterized the ellipse in its horizontal position. We can again employ the trick that we have used previously of interchanging x and y. Which results in the following equation. We'll get y squared over a squared plus x squared over b squared equals 1. And so this ellipse has foci oriented on the y-axis with coordinates 0 plus minus c, where c squared is a squared minus b squared. So note that a always denotes the longer axis, and vertices 0 plus minus a. So I should explain in some more detail that the values of a and b determine here the points, the intercepts. If you draw the ellipse like so. Okay. Suppose Okay, so suppose we have this ellipse here, then the coordinates of intercepts for ellipse with this equation are going to be so we have here and here the vertices. Oops. So this, in fact, this picture, in fact, corresponds to the first equation. Let me correct it for the second. The second equation we have rather so for the second equation here, we are in the situation like this. So the longer axis is oriented vertically, and the two vertices here have the coordinates of a0, 0a and 0 minus a, as observed here. And the x-intercepts have coordinates minus b0 and b minus 0. So that's easy to check. You just need to plug in 0 for y, which gives that x is equal to plus minus b, which is indeed what these 2 points are. So for the first situation, for the horizontal orientation of the ellipse, the longer axis is horizontal. In this case, for the vertical orientation, the longer axis is vertical. But in both cases, the quantities a and b determine the positions of the intercepts. And so to illustrate this, let us discuss similar type of questions to the ones we discussed for parabolas. So let us take an ellipse given by its equation. And so this is an ellipse. We have its equation. We're supposed to sketch it and locate its foci and vertices. And so the way to do it first is to bring this to the standard form. So given the equation 9x squared plus 16y squared equals 144, we want to divide both sides by 144. So fortunately, 144 is precisely the product of 9 and 16. So as a result of this division, we end up with x squared over 16 plus y squared over 9 equals 1. And so this is an ellipse. Notice that the coefficient next to x is larger, and so this must be the a, since a is always larger, the larger coefficient of the two, a and b. And so this is therefore a squared, this is b squared. And so we have that a equals 4, b equals 3, which gives that the c is equal to square root of 16 minus 9, so that's square root of 7. This allows us to locate the foci of this ellipse. Namely, we know that the longer axis corresponds to the x term, and so that means that this is a horizontally oriented ellipse. So the foci are to the left and to the right of the origin, and so then they have the coordinates plus minus square root of 7, 0. And likewise, the vertices have coordinates plus minus 4, 0. And then if we are to graph this ellipse, to sketch a graph of this ellipse, we would draw an ellipse that is elongated horizontally, like so. We would have something of this shape. And so here we have the two foci are inside the ellipse somewhere here. So this is √7, this is minus √7, this here is 4, and this is minus 4. We could, just for completeness of the picture, also denote the other two intercepts, which have coordinates plus minus b, 0 plus minus b. So that means we have 3 and minus 3 over here. So this completes the sketch of this ellipse. In general, you can always ask questions, say starting with the equation of an ellipse, go to its geometric properties, as we did in this question, or vice versa. Given the location of the foci and vertices of an ellipse, determine its equation. So clearly, by this discussion and by the formulas that we have here, knowing the position of foci and ellipses and vertices of an ellipse is enough to determine its equation. So you have this correspondence between the geometric properties and the equation of an ellipse.